Hello there. So this is video number 1 of section 6.2. The moment I'm still using the very outdated iPad for notes. But anyways, so remember in section 6.1, we introduced this sort of new operation called the dot product of two vectors. Remember, you basically just line up the entries of the vectors and then multiply the corresponding entries and then take the sum of all of those multiples. And so in doing that, we learned, of course, you can calculate the norm or the length of a vector in that way. You can calculate the distance of two vectors in that way. And then we introduced this idea of orthogonal vectors, which had a dot product of 0. And then we sort of showed that if you look at the angle between two orthogonal vectors, then that should form a 90-degree angle. So we're sort of going to continue with this idea of orthogonality in this section and actually quite a few sections moving forward. There are a lot of reasons to desire orthogonal vectors, or even, as we'll see later on, matrices whose entire column sets are orthogonal. And so we'll see sort of the reasons for that moving forward. But right off the bat, I want to introduce a new definition called an orthogonal set. And this is one of those nice definitions in math that I think is basically exactly describes what you think it should describe. That we say an orthogonal set of vectors u1 through up in Rn, like I said, is an orthogonal set if each pair of distinct vectors in the set is orthogonal. That is, if I take any two vectors in the set, of course we learned that the dot product of a vector in itself is only 0 if that vector is 0. But if I take any two vectors in the set that aren't the same and take their dot product, then that should equal 0. So I've just got two examples here. All we want to do with each of these two examples is determine if this set is orthogonal. And so all we have to do that is enumerate these vectors. So we'll say this is u1, u2, u3. This is, I guess we'll name these ones v1 through v3. And so to check each of these, we just have to check each of the pairs of dot products. If we've got a set of 3 vectors, there are a total of 3 pairs of vectors. Interesting, you can count that by, right? So if you have a set of 3 things and you want to count the number of ways to pair off 2 of those 3 things, right? It's actually easier to count not by pairs, but by which vector is not included, right? So if we're picking 2 things out of this set, every time I pick 2 things, I'm excluding 1 thing. Well, and each different thing being excluded defines a different pair. And so there's 3 ways to basically give me pairs of vectors. Kind of fun. So we want dot product of u1, u2, dot product of u2, u3, and dot product of u1, u3. And now I think some of these are 0. So for example, I think maybe this first one might be 0. I guess I've already given away the answer here, but so this would be -1 times 5 plus 2 times 4 plus -3 times 1. And so you can see this dot product is 0. But I believe if we did u1 times u3 maybe, and of course we can do these in any order really. Yeah, this one is gonna break, I think. So notice here we've got -3 minus 16 is -19, but -3 times -7 is 21, and so this is equal to 2. And so we would say that this set is not orthogonal. And again, the reasoning here is that every pair of vectors in this set has to be orthogonal, not just a few. So now we can test this set out. And again, we want to do v1.v2, v2.v3, and v1.v3. So v1.v2, 1 times 0 plus negative 2 times 1 plus 1 times 2. That one's pretty easy to see. That's 0, 0, and then we've got the same product but negatives of each other. 0 is such a nice number. And then actually the same thing happens with v2 and v3. It's almost like these vectors were defined in a way to make them orthogonal. Oh, actually no, these are not going to be orthogonal. No, these are. Sorry. So then we've got 1 times negative 5 plus negative 2 times negative 2 plus 1 times 1. This one was a little less obviously orthogonal. So this is negative 5 plus 4 plus 1 is 0. That's good. I wanted one example of orthogonal and one example of not. And so this would be considered an orthogonal set for this reason. So when we have orthogonal sets, what else do we know about them? That's what we're going to investigate a little further in this video. So the first thing we know about an orthogonal set, and we will prove this theorem, is that if we have an orthogonal set of vectors, then it must also be a linearly independent set of vectors. And remember, once we sort of cross that threshold of being linearly independent, we learn a lot about our set of vectors. So this is theorem 4. That if S, I guess I could have left the vector set notation up on the board, but if S is a set of p vectors and is orthogonal, and we'll say of non-zero vectors in Rn. And so of course here we need to specify non-zero because we're trying to show this set is going to be linearly independent. Then S is linearly independent. And your book adds this, but the second part just follows from the invertible matrix theorem or from any one of those theorems, and hence a basis. I guess that's not the invertible matrix theorem. Well, it could be in a way for the subspace spanned by S, meaning basically this is just a, whatever. This sentence isn't saying too much other than the fact that this is a linearly independent set of vectors, and if we take its span, then of course it's a linearly independent set that spans whatever set it spans, and so this is a basis. Because remember, the span of any set of vectors is always a subspace, and so certainly then if that set of vectors is itself linearly independent, that defines us a basis. All right, so we're going to prove this theorem using contradiction. So what is the contradiction we want to arrive at? And of course, with a lot of these now, I've got sort of a, if you want to work this proof out for yourself, I've got sort of, again, the steps that you would use, and I highly recommend trying to do that because it's fun and it's good practice. Okay, so we're going to assume that S is orthogonal. But we'll say for the purpose of contradiction, meaning basically we're assuming this next part to eventually arrive at a contradiction. We're going to assume that S is linearly dependent. And so, of course, this means there exists constant C1 through Cp, and not all of these are equal to 0. Such that the 0 vector is equal to C1, U1 plus C2, U2 plus Cp, Up. And so eventually now we're going to see why the property of being orthogonal is so powerful. So we're going to let C sub I be the smallest indexed vector. Or actually, I guess to shorten it, I'll say the first vector, or C sub I is a scalar, so the first scalar that is non-zero. And so all this is saying is, remember, in this sum, some of these scalars might be 0, right? Like, it's okay for some of these scalars in this dependence relation to be 0, but we just know that some of them aren't. And so what I'm saying is we're just going to take the first one. And it actually, for the purpose of this, it doesn't really matter as long as we're taking any non-zero one. So what we're going to do is multiply, and I'll call this equation 1. I guess I'm calling this 1. I'll call this equation A. Equation A by the vector u sub I. So what do we get? And actually, it's not multiplying, sorry. We're going to take the dot product on both sides. So dot product A by u sub I. So we get u sub I dot product 0, which is just equal to 0. Right? So notice anything dot product with the 0 vector is equal to 0 is equal to, well, u sub I dot product of this entire vector sum. But remember, by the properties of the dot product and vectors, right, I can distribute this u sub I through and factor out scalars. And consider the individual dot products of u sub I in each of these vectors. Right, so all I've done is multiply both sides by this vector u sub I corresponding to the non-zero scalar c. And now I've gotten 0 on the left and distributed this all the way through. But remember, we've already assumed, and this is the thing that we are assuming, that S is an orthogonal set. That means that everything here is equal to 0 except the dot product of u sub I with itself. And this is equal to 0. And so now we are beginning to arrive at our contradiction, because we know that C sub I is non-zero, right? So I've got one non-zero thing, but I've also assumed that all of the vectors in my set S are non-zero. And remember, the dot product of a vector in itself is only 0 if that vector is 0. So I've just managed to show that something that is definitively not 0 is equal to something that is definitively 0. And that's maybe one of the biggest contradictions you can arrive to in math, that 0 is definitely not equal to anything other than 0. And so this is a contradiction. So why does this prove the theorem? Well, we started out by assuming S was orthogonal, right? And so what we just showed is that if S is orthogonal, there's no way that it can also be linearly dependent. That means it is linearly independent, and that proves the theorem. So moving forward from this, we can sort of introduce a new definition now in light of this, knowing that, of course, an orthogonal set is also linearly independent. We can define what is called an orthogonal basis, and hence continue the trend of using definitions or using terms for our definitions that make a lot of sense, because an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. So fairly straightforward. So given this type of a definition, and of course we know this is possible by the previous theorem 4, right? That since every orthogonal set is linearly independent, really the only hurdle now, if we started out with an orthogonal set in order to find a basis, would be to make it linearly independent. And like I said, moving forward, we'll eventually see why we want orthogonal sets or orthogonal columns or orthogonal bases in general. They possess some very nice properties. So what's actually immediately we'll see one nice application, that if we have an orthogonal basis, we actually know how to calculate the coordinate vectors for each vector in our subspace. So what that means is that if we've got some orthogonal basis u1 through u sub p of any subspace, of Rn, and we take any vector in Rn, so when we just take a vector y, sorry, not in Rn, in W. Of course, y is also in Rn, but we have to specify that y is in this set for which this is a basis. What we also know, well, since this set is a basis, right, we know that y can be written as a linear combination of the vectors in this set. But what we also know, and this is the interesting thing, and one reason why orthogonal bases are nice, is actually we also know the values of all of these constants. And so this will be a little weird, but this is equal to y dot product uj over uj dot product uj for all j. And it turns out the proof to this is very straightforward. So what this means is that if we've got an orthogonal basis, right, and remember a lot of problems we've seen deal with actually finding these constants, right? So being able to express y in terms of a linear combination of our basis vectors. We've spent a lot of time already in this course, solving this problem here. And so normally what we would have to do is, set up an augmented matrix. Maybe we could use a, factorization, an LU factorization, or something like that to shorten the problem. But this says, and especially if you were programming an algorithm to do this, this is just two dot products and then a fraction for all of these scalars, right? So you could calculate each one of these scalars very quickly and then, have the coordinate vector for y calculated very quickly. This would just be a few multiplications and some addition. And so the reasoning actually behind this proof, I think, is very cool, and can be done in just a short amount of space. And I'm going to call this a proof because what I'm going to do is I'm going to show that it's true when j equals 1. So basically we're going to solve for C1 in this equation. But then I'll explain that after this, basically. We'll see that the way we solve for C1 can be used to solve for C sub j for all of these constants. And so the way we do this, well, multiply basically it's kind of the same proof that we just did. I keep saying multiply. Take the dot product. So we want a dot product both sides by u1. And so that gets us u1 dot product y is equal to u1 dot product c1 u1 plus cp sub up. And now you maybe can kind of see where this is going, right? I can distribute this u1 to this entire sum, much like I did in the previous proof. But in distributing u1, remember, u1 is orthogonal to every vector in this set except itself. So this means that u1 dot y is equal to u1 dot c1 times u1. Well, and now notice I can pull this c1 out and divide by u1 dot u1 to get that c1 is equal to u1 dot y over u1 dot u1. And so notice that this exact process could have been used for every single vector in this sum by just multiplying this equation by, say, if I wanted to solve for c sub j, or sorry, I keep saying multiply, take the dot product of uj with this equation, and then you'd be left with cj, right? Because everything else would cancel out except for the vector that you took the dot product, that you used to take the dot product of both sides. So that's sort of one nice quality of orthogonal bases. Of course, we'll see many more moving forward. And so I just want to end this video now with the example that is in the worksheet. Basically, we're just going to put, we're going to apply theorem 5 to a real example and kind of show how it can be useful. Of course, with a lot of things we've introduced, this might seem to take a little longer than just, kind of solving the normal augmented matrix equation. But, certainly there could be uses for this if, maybe we were working in slightly higher dimension, but once you get to high enough dimension, it just becomes tedious to do it by hand. So let u1, u2 be an orthogonal basis. For R2, where u1 is this vector, 2, -3, and u2 is 6, 4. And you can take my word for it that these are orthogonal, but I think I would believe that they are. And so now we want to, I think I forgot to define x. Let me see. I know I pulled this problem out of the book, so let me see if I can figure out what x should be. -3 and 6, 4. Ah, there it is. Okay. Let x. I'll fix that in the worksheet before posting it. But I forgot to define what x was in the initial worksheet. And so we want to express x as a linear combination of u1 and u2. Meaning, basically what we want to do is calculate constants c2 and c1 in this equation. So our newest theorem tells us that c1 is equal to x dot u1 over u1 dot u1, and that c2 is equal to x dot u2 over u2 dot u2. And so x dot u1, if you do the calculation, is 18 plus 21 is 39. u1 dot u1 is 4 plus 9, so 13. So c1 is equal to 3. X dot u2 is equal to 54 minus 28 over u2 dot u2, 36 plus 16 is 52. So that's 36 over 52 equals 1/2. And so x is equal to 3u1 plus 1/2 u2. And so as you can see, having this nice property of an orthogonal basis means that if we wanted to, we could calculate these scalars in this type of an equation very quickly. So that wraps up video 1 of this worksheet, or video 1 of this section. So next we will learn about orthogonal projections, which is where this starts to get really cool.